Josephine Kalende from Group 31, and I'm going to be talking about graph reasoning computational modeling for conception probability estimation using heterogeneous data. So, the background and introduction. Traditional fertility prediction methods such as calendar tracking and ovulation kits offer limited personalization and accuracy. These approaches often fail to integrate hormonal, lifestyle, and temporal data, leading to poor generalization. The rise of digital health and machine learning enables more dynamic, data-driven fertility modeling. There is a growing need for multi-factor psychoindex prediction that accounts for individual physiology, lifestyle, and treatment effects. So for our keywords, we have conception probability prediction. This is the estimating of likelihood of a woman to conceive based on medical and lifestyle data. Then knowledge graph reasoning. This is the using of network entities and their relationships to make logical inferences. Then we have fertility and reproductive health. Fertility is the ability to conceive. Then reproductive health is the overall health of the reproductive system. Then you have survival and causal modeling. Survival modeling predicts the time until a specific event occurs. For example, the next time until the next cycle. Then causal modeling identifies the cause and effect relationships between factors affecting fertility. Then we have computational fertility. This is the using of computational models, simulations, and AI to analyze fertility data and make predictions. So for related works, to ground our work, we reviewed several key papers, and then this table summarizes the different models like convolutional neural networks, relational neural networks, random forests, and other graph-based architectures like graph convolutional networks and relational graph convolutional networks. So we noted their strengths like high accuracy and their ability to handle multimodal relation graphs. Then we also noted their limitations like lack of temporal awareness and poor interpretability. These all helped us to shape our modeling choices. So we have the problem statement. We have the domain application problem and computational problem. The domain application problem, we have predicting cycle-level computational outcomes is essential for personalized fertility planning and treatment guidance. Existing systems lack temporal granularity, clinical interpretability, and treatment-aware modeling, limiting their utility in real-world settings. Patients and clinicians need actionable predictions that reflect hormonal profiles, lifestyle factors, and psychodynamics with the support of counterfactual reasoning and subgroup fairness. Computational problem. How to model multimodal psychoindex and graph structured data for conception prediction across diverse patient cohorts. Then you have how to integrate temporal patterns, causal effects, and uncertainty quantifications into unified pipeline that supports real-time inference. Then you have how to ensure fairness, calibration, privacy-preserving deployment, especially across age, BMI, and lifestyle subgroups. Then you have how to benchmark and refine models using external calibrations and subgroup calibration audits. Then we have the research question and objectives. The research objectives, we have to design a multimodal AI pipeline for cycle-level conception probability estimation. Then we have to integrate mechanistic, temporal, and graph-based features into a unified modeling framework. Then we have to evaluate model performance using calibrated metrics across patient cohorts. Then we have to estimate individual treatments using causal inference techniques. Then we have to audit model fairness across age, BMI, lifestyle subgroups using calibrations and sharp explanations. Then our research contribution, we built a graph temporal causal pipeline for conception prediction. We fused 5 graph embeddings with transformer and T-learner. Then we modeled cycle-wise dynamics and estimated treatment effects. We audited fairness and calibration across the different subgroups. Then we deployed a modular API-ready prediction system. Our outputs included a validated model, a custom knowledge graph, then the conceived score products with real-time IT estimations. Then we also had the open source notebooks. So for our methodology and system architecture, we harmonized the raw data into cycle index tables, and then after harmonizing the data into cycle index tables, we were able to run strict temporal cohorts. This was to ensure that there was no leakage from future values. Then we were able to engineer mechanistic features like ovulatory competence and comorbidity burden. Then we were able to construct the knowledge graphs. This was to incorporate structure in our system. Then with node types, we had node types like biomarkers and treatment outcomes. The edges encode causal and physiological relationships. Then we used embedding techniques like real graph stage and rotate embeddings, and we turned the knowledge graphs into numerical representations, and then the embeddings encode how features relate with each other. So after that, we were able to fit different models like light gradient boosting model and the temporal transfer, and then we carried out hybrid stacking on them. Then we fitted other temporal models like relational graph convolution networks, graph convolution network, and others. Then after that, we carried out late fusion on them. Then to address causality, we carried out causal inference modeling using structured causal modeling and IIT estimations, and then we were able to come out with the evaluation metrics and calibrations. So for our model architecture and mathematical foundations, our different models carried the different knowledge graph embeddings and used them to estimate the likelihood of conception. So for our dataset description and exploratory data analysis, we had 20,000 records in total, and then we had both categorical and numeric columns. We sourced all our data from mainly the dataset, and then for our exploratory data analysis highlights, we were able to join the different datasets. We filled in the missing values, then we explored both categorical and numeric features. We encoded the categorical data to numeric features, and then we plotted the feature coloration heat maps. This was to show how different features correlate with each other. This helped us identify clusters to related variables, and then we plotted categorical variables. This helped us in subgroup fairness audits, and also helped us to understand how different factors influence conception. We also constructed the knowledge graphs. Then we have the results and discussions. We have the results of the training, validation, and testing sets of the light gradient boosting, the temporal transformer, and their meta model. So the light gradient boosting model showed strong training performance, but then the performance dropped at the validation and testing state. Then the temporal transformer model had overfitting. Then for the other temporal models, the graph neuron, we had relational graph convolution networks, graph attention networks, temporal graph networks, and variational graph encoder, plus graph isomorphism network. So we evaluated the 4 unsupervised graph embedding models for conception prediction using logistic regression across all models. The area under curve remained at 0.5, indicating no discriminative power. The F1 and precision scores were consistently moderate, suggesting that the models predicted a single class reliably but failed to rank conception of likelihood. Then These results highlight a key limitation. Unsupervised graph embeddings alone do not compute predictive fertility. Then, to improve performance, future work should explore supervised graph learning integration with temporal models. Then we carried out late fusion on those models, and then this helped us to improve interpretability, but this struggled with generalization. And then we have the validation and generalization results with a nested cross validation with 3 folds, and then we have the overall summary of the different validations. Then after that, we carried out subgroup calibrations, and these were to ensure subgroup calibrations. These were to check whether the model performs equally well across different subgroups like the age quartile and the BMI quartile. And then we had the IPW model set evaluation. The validation of the area under curve is moderate, and then the test drops sharply. Then for the sharp analysis, we noticed that the progesterone and E2 are consistently top-ranked across the different age groups. E2 becomes increasingly dominant in the older age groups. Then the cycle timing features, we have fertile window ovulatory competence. This gain importance in the middle age. Age itself has a low direct impact on conception. So for the model deployment, we deployed the late fusion model. For our justification, it combines structural perspectives from the 5 graph embeddings, and then the model's temporal and counterfactual dynamics across menstrual cycles. Then it supports individualized treatment effects estimation via T-learner, demonstrates strong calibration and fairness in validation audits, then outperforms baseline models in subgroup reliability and interpretability. Then the technical justification, modular design supports late fusion, uncertainty quantification, and causal weighting. Compatibility with real-time inference, API development, and sharp-based feature. The deployment pipeline, we carried out data ingestion, we carried out preprocessing, model training, evaluation, and then deployment. So, demonstration of the developed product. Our product is the concept score, and it predicts cycle level conception probability and estimates individual treatment effects. So, the limitations, we have the architectural limitations, like graph models. These were sensitive to graph sparsity and edge noise. Then the transformer head, it requires large diverse cycle sequences for robust temporal learning. Then the T-learner, causal inference model, it assumes balanced treatment groups and strong covariate overlap. Then the data limitations, we had missing labels in the demo. Then we had limited cycle diversity. For the lifestyle feature imbalance, then we had underrepresentation of certain lifestyle factors like alcohol use, stress variations. And then for system level limitations, we had overfitting in the training and validation splits. Then we had limited external validations, and then calibration drift across the subgroups. So in conclusion, we developed a graph temporal causal pipeline for conception prediction using late fusion model. Then we integrated mechanistic features, lifestyle factors, and psychoindex dynamics to enhance interpretability. He achieved a strong calibration and subgroup fairness across